Now I'll do the examples of these two molecules, proton NMRs. I want you to I think it really helps for you guys to see me labeling them because you're going to be doing the same thing. And the more you see of this, just everything starts to make sense. So here we have 1,1-dichloryl 2,2-diethoxyethane. So let's number this just so you can see where the naming comes from. That's carbon 1 and that's carbon 2. So you can see carbon 1 has 2 chlorines on it, so 1,1-dichloryl. And then carbon 2 has these ethoxys. See, this is 2 carbons, an ethyl, and it's got an oxygen there. So it's an ethoxy, and you got 2 of them, 2,2-diethoxy. And it's ethane because it's 2 carbon parent chain there. This isn't something you're expected to name yet, but I just pointed out. We'll get to those later. And then this one here is 1,1,2-trichloropropane. So if I number the carbons from the, and this time from the right to left, the way it's drawn, carbon 1 has 2 chlorines, and carbon 2 has 1 chlorine, so that's why we say 1,1,2-trichloral. And it's a propane because if you count the parent chain, the longest chain is 1, 2, 3 carbons long. Again, you wouldn't be expected to name this for a long time, so just pointing it out. All right, here we go. We're going to follow my instructions to label this. I gave you the expanded molecular formula here. And the first thing I asked you to do is to draw the molecule and the bond line structure on the spectra. So we got some room right there. Hopefully that's where you drew yours. And you can see when I draw in the bond line structure, it's just so much cleaner and easier to see. I really like these, and we're going to be primarily using these type of bond line structures, not so much doing the expanded stuff. So the next thing to do is to circle your equivalent groups of hydrogens. There's one hydrogen there that's unique, another one hydrogen here that's unique, and then these methylenes, CH2, CH2, these 2 hydrogens here, 2 hydrogens there, they're equivalent. You can see how they see the same thing. It's kind of harder to see in this drawing, huh? And then the methyls at the end are equivalent. Okay, and then next I ask you to label the spectra, and I always want you to label it from the most downfield signal, which is the signal to the left. We call that A, and then the next would be B, C, D, and then after that we'll label the TMS as well. Okay, now let's assign these letters to the groups of hydrogens we circled. So we have a 1 hydrogen signal and a 1 hydrogen signal, and then so they're these guys. There's no way we would know just from this spectra that A is that one and B is that one, but I did give you the spectra with color on it. So you're not expected to know that, like, for example, that one's A and that one's B. If I gave you a question like this on the exam, and you would probably put A or B here, or B or A there. So, but that's what it is. And then C, though, you should be able to label that because it's 4 hydrogens, and this is the only 4 hydrogen group. So there's C. And then D you should be able to label because it's 6 hydrogens, and that's 6. So there we go. And lastly, we'll add the coupling prediction. So this signal A, it only sees this one neighbor. These other neighbors are too far away. So if it sees one neighbor, n+1 rule, it's a doublet. B will see the neighbor on A, but will it see the neighbor on C? Let's see, we have to go through, imagine hydrogen here. 1, 2, 3, 4 bonds away, too far. They're all single bonds, long single bonds. So that's a 1 hydrogen doublet. And you can see that on the spectra as well. That's nice, right? And now signal C, I'm going to use this as a representative. Can it see these neighbors? Let's see, 1, 2, 3 bonds away. Yeah, so you can see all 3 of those neighbors. So this right here will be a quartet. This over here is also going to see 3 neighbors. It'll be a quartet. And a lot of times people get confused with this, but these 2 hydrogens will not see those neighbors. It'll only see its neighbors. So this is a 2 hydrogen quartet. This is a 2 hydrogen quartet. They're equivalent, so they overlap to make a 4 hydrogen quartet. And all those their neighbors are equivalent. That's why it's not a quartet or something. We'll see examples like that next. All right, and then D here, each of these methyls sees just 2 neighbors. So 2 + 1 is a triplet. So this is a 3 hydrogen triplet, 3 hydrogen triplet. They're equivalent, so they overlap, and we call them a 6 hydrogen triplet. That's what we have here. So that one's done, not too bad, huh? And on this one we had a coupling that was more straightforward because all the coupling involved neighbors that were equivalent to each other. This next one, we'll see the coupling will be a little more complicated. But we'll start off the same again. We'll first draw the molecule and its bond line structure. Here it is. You can see the bond line structure a lot cleaner, huh? I really like these bond line structures. I remember when I first learned about them like you, I thought, oh, these are pretty cool, the way it just simplifies everything. Now we'll circle our groups of hydrogens. We have a 3 hydrogen signal here, 1 hydrogen signal that's unique to this one. That's another 1 hydrogen signal. These are not equivalent because this 1 hydrogen signal is on a carbon with a single chlorine, where this 1 hydrogen signal is on a carbon with 2 chlorines. You could tell they're different. And now let's label our signals from downfield A. And this A signal, when I first just look at it here, it looks like it might be a singlet, but we zoomed in on it and you can see it's actually a doublet. So you see how it's a little past, or almost to 6 parts per million, and you zoomed in, there it is, almost to 6 parts per million, like 5.85 parts per million about. Okay, and then next up is B. And we zoomed in on B as well. And you can see B is pretty complex, huh? It's not a simple like doublet like this initial one. We'll talk about that. And then over here we have C. It looks like a singlet, but if you zoom in on it, you can see it's actually a doublet. And finally, there's the TMS at 0. We set TMS to 0. And all of our other chemical shifts, like this guy being at about 1.7 parts per million, is relative to TMS at 0. Okay, so now let's label predict and the coupling and see if it matches. So this 3 hydrogen signal here should have 1 neighbor, just this neighbor. Will it reach this neighbor over here? Let's look. 1, 2, 3, 4. 4 bonds away, but it's all through long single bonds. So nope, it won't couple to those. It should just have 1 neighbor, so N plus 1. This should be a 3 hydrogen. Oh, that's signal C actually, sorry. Oh, I got ahead of myself. That's okay. Well, that we'll see as a 3 hydrogen doublet. But let's go ahead and notice that there's 3 hydrogen, largest area signal. It's going to be C, and it is a doublet. And then this 1 hydrogen right here, which one would it be? Will it be A or B? I know I've color coded it already, but you can tell that it should have 3 neighbors over here and 1 neighbor there. So 4 neighbors. Should it be the doublet one? No, it should be B, the one that's complex. And then finally this one has only 1 neighbor, 1, 2, 3 bonds away, so it's going to be the A signal. Okay, so now back to the coupling. So we said C would be a 3 hydrogen doublet because it only sees this 1 neighbor, and look at that, it's a doublet. B though, that's an interesting one. 3 neighbors here, 1 neighbor there. Those neighbors are not equivalent to each other. So even though it has 4 neighbors total, which N plus 1 would make it a pentat, it's probably not going to look like a pentat, but we're still going to label it that way. We're going to call it a 1 hydrogen pentat. Like, I don't know, maybe a pentat? Sometimes these will come out to be what their simple coupling would be, but not this one. Pentat would have 5 peaks to it. This one has maybe like 1, 2, 3, 4, 5, 6, 7, 8, I think. So yeah, this one didn't turn out to be a pentat, but that's how we'll label, that's how we'll predict it and label it. All right, now A is a better one. It's got just 1 neighbor there, so N plus 1 is a doublet. So we should have a 1 hydrogen doublet, and what do you see? A doublet. Nice, right? Okay, good job. Now back to the Google Doc spectroscopy intro.